Okay, welcome back to our lessons in organic chemistry. So today we're going to take a look at the second half of our look at functional groups. You'll remember that functional groups are parts of an organic molecule where kind of the interesting chemistry happens, where the interesting reactivity occurs. Now the first thing we're going to look at is actually not technically a functional group, but since it does affect the reactivity of the chemicals, we're going to kind of lump it in with functional groups. And we're talking about isomers, and we've already talked a little bit about different structural isomers, and we know that there are structures that have the same formula but different chemical structures and then therefore different chemical properties. So as the number of carbons in the carbon chain increases, the number of isomers increases as well. And there can be quite a few for our longer carbon chains. So for example, pentane is a fairly straightforward alkane. Pentane would just be 1, 2, 3, 4, 5. There's our pentane molecule that we know quite well. And methylbutane has the same, 2-methylbutane, 2-methylbutane are isomers. And so methylbutane would be 1, 2, 3, 4 with a methyl group here. If you counted up all the carbons, you would count 5 carbons, and you would count 12 hydrogens. And if you did the same thing here for your 2-methylbutane, you'd count 5 carbons and 12 hydrogens. So there is one more structural isomer, which could be, say, propane with 2 methyl groups. And so we would have a 2,2-dimethyl propane. Now again, this is C5H12, and these are the isomers that we're familiar with. It's fairly obvious that these are going to have different properties because their structures are quite clearly different. But we're going to talk about one other kind of isomerism that maybe isn't quite so clear from the get-go. And this is something called Sis Trans Isomerism. So we're going to draw, it says here, draw the structure for 2-butene. Okay, and I'm going to draw the full structure. So 2-butene would have 4 carbons, so I'm going to have a CH3 attached to a C, which is double bonded to another C, which is double bonded to a CH3, and I guess each of these carbons also has hydrogens attached to them. So the way I've drawn that there, you can see 1, 2, 3, 4 carbons in my chain. That makes it butane, and because the second carbon has a double bond to the third carbon, it's 2-butene. But where I placed these hydrogens was just sort of haphazard. For example, I could have drawn my structure like this. I could have drawn a CH3 attached to a carbon, double bond to another carbon, and then I could have gone this way with my branch to my next CH3, and then my hydrogens would be here. Now, at first glance, this doesn't look like maybe it's any different, but I just want to show a quick example here. So if we take a look, these are the two examples that I just drew. And you can see here that these two examples are in fact structurally different from each other because of this double bond. Now remember that single bonds are going to be able to spin freely, and so where you place these hydrogens doesn't matter because as this atom spins around this double bond, it can be in any orientation. But this double bond isn't going to work like that. It's going to lock these two carbons in place, and so they're no longer free to rotate. And so as I move this around and look at it from different angles, I can see that this, if you want to think of these two carbons as being like methyl groups, they're both kind of sticking off, let's say upwards or downwards. It doesn't matter which way we orient it. Whereas when I look over here and I look across this double bond, if I imagine like an imaginary line that goes across here with a double bond, one of the methyl groups is kind of up and the other methyl group is down. And again, it doesn't matter which way we orient this. You can see that they're never going to be kind of on the same side of the double bond as each other. And that's what we call cis trans isomerism. So this all happens because the double bond locks or effectively locks the molecule in place. And so the atoms are no longer able to rotate around that bond. And it's worth noting that these can only happen in alkenes. So they can't happen in alkanes because single bonds can always freely rotate. And they can't happen in alkynes because if you have a triple bond, well then there's no second group to worry about attached to the other carbon. We'll see some examples in a second. When it comes to naming these things, so remember the parent chain must contain the double bond, just like it would for any alkene. And if the molecule is cis, which means same side, or trans, meaning opposite side, at the double bond, and that's going to be the key there, then we're going to include that in front of the parent chain. Okay, and we're also going to, of course, include the number of the carbon where the double bond starts, just like we would for any other alkene. So let's take this first example here. So I've got, first thing I identify is my parent chain. You can see I've got my parent chain right here. That's fairly clear. I'm going to number it in a way that's going to make the double bond the lowest possible number. And so that would be 1, 2, 3, 4, 5. And then I'm going to start to name it. So it's a 1, 2, 3, 4. It's a 5 carbon chain. So this is going to be a bute. It is a double bond there. So it's a butene. And the double bond happens on the number 2 carbon. Now I just need to specify whether it's cis or trans. And so just imagine we've got a line here that extends across our double bond. So imagine that plane of that line. And then ask yourself, are the two alkyl groups, are they on the same side of that line or are they on opposite sides of the line? We can see here that they're on opposite sides of the line. So this would in fact be cis. Pardon me. It would be the exact opposite of that. It will be trans to butene because they're on opposite sides. All right, let's take a look at another one here. So I've got, again, identify my carbon. My parent chain is going to be this one. And then I will number these off as 1, 2, 3, 4, 5, 6, 7. So it must be a heptene. It's a 2-heptene on the number 2 carbon. And then just picturing this plane here cutting across my double bond, I can see that these two parts of the carbon chain, if you want to think of them like alkyl groups, are on the same side of the double bond. So this is a cis 2-heptene. All right, so we're going to look at just 3 more examples of actual functional groups. And these are going to be quite similar to the functional groups we saw last time, like alcohols and ketones, but really they're going to be kind of combinations of these things. We're going to start to kind of put them together. And so a carboxylic acid is the first one we're going to look at. And the general formula for that is some R with a carbon with a double bond to oxygen, which is also bonded to an OH. You could almost think of this as being kind of like an aldehyde, but also a terminal alcohol all at the same time, where it's got the double bond oxygen, but also an OH attached to it. And this is going to be something that contains a carboxyl group. So as we've started to see in organic chemistry, some of these things, this C double bond OOH, this gets a special name called a carboxyl group. And anytime you see that. So the parent chain must contain the carboxyl group. And to name it, we're going to replace the E at the end of the parent chain with oic acid. So let's take a look at a couple of examples. I've got this one here. Now, just notice when we draw the skeletal structure, we've drawn these oxygens. The carbons are just here and here. So the parent chain here is actually only a 2-carbon chain. There's 2 carbons. Don't count this OH here as a carbon. And so this will be an F. And since it's all single bonds, it's an ethane. But since it's a carboxylic acid, we'll call it ethanoic, and then the word acid. Now, ethanoic acid is actually something you're quite familiar with because its common name is actually acetic acid, which we've seen a bunch this year because it's that component of vinegar. If you remember how ethanoic or acetic acid is often written, it's often written as CH3COOH. And we talked about that earlier this year, like why would you bother writing this COOH separate from this other one? Why not just group all the carbons together and group all the hydrogens? And that's why, because it's telling you that when you put them together in this way, you're making a carboxylic acid. All right, so for this next one here, we've got, let's see, we've got a carbon. Now, our parent chain is fairly obvious here. It's this long one here. Something we didn't mention is where do we start numbering from? And so we should number our carbon so that the number 1 carbon is the carboxyl carbon. So this is actually carbon number 1, 2, 3, 4, 5, and so on. And so when it comes to my name, it's a 5 carbon, and so I guess that is going to be a pentane, but it's a carboxylic acid, so it's a pentanoic acid. Now don't forget that I do have this this group sticking off the side here. I do have a methyl group, so I should mention that it is a 2-methyl pentanoic acid. All right, we got 2 more functional groups coming up. The next one is an ester. And the general formula for an ester is going to be some R chain with a carbon. And then it's going to have a carboxyl group. So it's going to have the same as that that we saw with carboxylic acid. Except in this case, instead of it being attached to an OH, we're going to replace this H with a whole new carbon chain. And so this is an organic compound consisting of a carboxylic acid where the OH is replaced with an OR. So there's a whole new carbon chain attached to that oxygen. The parent chain is going to be the one with the carboxylic group. So just like we saw with carboxylic acids, you're going to replace the E of the parent chain with O8. And the carbon chain, which is attached to the oxygen, is just named as an alkyl group. So that probably doesn't make a ton of sense. So let's look at a few examples. Okay, our parent chain here is going to be this one because it is the carbon that is it's the carbon that is attached to the carboxyl group. I don't need to number them, although if I was going to number them, that would be my 1, 2, 3, 4, 5, and so on. But I don't have any branches, so I don't really need to worry about numbering. So the parent chain is a pentanoate. And then this is the alkyl group, which is attached to it. And I can see that it's a 2-carbon chain. And so that would be an ethyl group. So ethyl pentanoate. Take a look at this second example. Now deciding on the parent chain is maybe not as immediately obvious. There is 2 carbons over here and a single carbon there, but this is the parent chain. It's the parent chain because it is the one that is attached to the carboxyl group. And so this is a methanoate, just a single carbon. Whereas this is my alkyl group and it's a 2-carbon chain, so that it is an ethyl. Ethyl methanoate. Okay, last but not least, we are going to look at ethers. And an ether is going to have the format where it's going to be some R chain, so some carbon chain, attached directly to an oxygen, which is then directly attached to some other carbon chain. So it consists of 2 alkyl groups bonded to an oxygen. And so the difference here is that the oxygen is right in the chain. It's part of the chain. Okay, so we're going to name both alkyl groups and then just follow it by the word ether. Okay, and it doesn't really matter. We'll just put them in alphabetical order. Okay, so I've got, this is one of my alkyl groups and this is one of my other alkyl groups. So I can see this is a methyl group, whereas this is a propyl group. So M comes before P. I'll just call this methyl, propyl, ether. And for my second example here, I can see that I've got a ethyl group on this side and an ethyl group on that side. I guess I could call it ethyl ether, but that is kind of annoying to say. So just to simplify things, I'm going to call it diethyl ether. Okay, that's it for functional groups.